Yeah, now all of your voices now will be captured. Maybe I should turn it so you can all get captured. Okay, so this is just a very simple example, and I'm going to delete most of it so that I can show you exactly how each part is done. And this is what the block diagram looks like if we actually do that fancy Windows 7 thing and do it this way. Okay, so this is the block diagram. This is essentially your back end. And this is your user interface. This is what you see when you're running the program. This is a really simple program just so that I can show you how nested protocols work. So this is a for loop, and a for loop is essentially a loop which will run as many times as you say n. So it keeps running for n number of loops. In for loops, you always have a loop iteration thing, and if you hover over it, it tells you what it is. A loop iteration tells you what number of the loop you're currently on. And there's a few other things in here, but I'm going to delete them all so we can build it at the same time. So we're going to trash it all. Bye-bye. Don't save. That's great. Let's do this. Okay, we have nothing now. Okay, so what I want to do is just show you very, very simple inputs and outputs, and then we'll move on to this example, which actually uses an image. So first of all, you right-click and you get this. These are all of your tools, essentially. They come into various categories: programming, measurement, and here's your vision toolbox. But you have a whole series of things. But what we want to do to start off with is, like the example was, it just displays numbers in a for loop. So what we're just going to do is create a for loop. You get a little box, you kind of draw it. Okay, that's a for loop, and we're going to run this for loop 100 times. So this loop is going to get run 100 times. Right now,
why?
Because I'm just showing you what a loop is. Do you want me to change how many times it runs? So instead of putting that number there, what we'll do is we'll go to the front panel. We'll in fact let you choose how many times you make this thing run. So we'll put a numeric control. We'll call this number of iterations. Okay, and as you saw, as I put this here, it showed up here. So this is what you see, and this is the block diagram version of this. Everything that's inside this loop will get run during the loop, so we don't want to have that running inside. We want to have it running outside. So we just wire this button into here. Okay, and so if you can, well, it's quite a little bit hard to see this little red dot. But what that little red dot means is that we've inputted the wrong type. So we're putting a double point precision number into an integer variable. The red dot means that it's wrong, but it's runnable. So it's the wrong type of number, but it will run it anyway because it'll basically disregard the things that make it wrong. So if you put in 12.3, it'll run it as 12. If you put in 12.65, it'll run it as 13. It's basically saying, look, I'm expecting an integer, and you're going to give me some number that's not an integer. So, but it can still work with it. The way to get around it is you change how the data is represented. So we change this from a double point precision to some integer. Let's change it to a 32 integer. Okay, so now the red dot's gone away, which now says, look, an integer is great. I don't mind any integer. That's great. So, okay, we now have...
I have a question.
Yes.
So, actually, what did you change now?
So I changed how the data is represented. So, if you have, there's lots of ways. Let me highlight this and we can go through it. So if you right click on it and go to how the data is, how it's shown and how to interpret the number.
Okay.
So there are lots of different types of numbers. They can be integer only. So I is, integer. U is unsigned, meaning that it's still an integer, but it won't wrap around the number. If you use, let's say, an 8-bit integer, like a grayscale image, it's 256, so that's an 8-bit integer. As soon as you get a number bigger than 256, it goes back to 0, because the numbers cannot be bigger than 256. Which is why I switched it to an sorry?
255 in that case.
Only if you start at 0. If you go to 32, it's whatever, 64,000. So you have a lot more numbers to choose from. Sometimes...
Even much more.
Yeah, 16 bits, yeah, okay. But if there are times where you don't want integers, if you're actually measuring something, you might want it to be 12.73. And the same thing when you're having multiplication and division, or any mathematical operation. Normally it's not good to use integers because you're rounding things off, and sometimes you want to know the exact numbers. So, but here, because it's an input, and we're inputting how many times we want to go around, we need an integer. But like I said, like I showed, we can put a different number in, and it'll still run. It's just it will round to the nearest number from whatever number we put in. So let's go back to our 32 bits. Anyway, okay. So then we can choose, whatever we want to do in our little box. So let's do something simple, and let's just add a couple of numbers together. So I, which is the loop iteration, well, we're going to add I to another number. So we're just going to go back here and put numeric control. And we're just going to call this the start number. Okay, so what I'm doing is dragging it outside of the loop because I don't want it to read this every time it goes around the loop. Because this is a number that we're going to put in on our user interface. So as this for loop is running, I don't want it to be reading a control unnecessarily. We can have it.
You could do it.
Yes, but I wouldn't be if that was something we wanted to do. It's probably better to run it in a while loop than a for loop. Because the for loop, we're essentially going to let it run. Whereas a while loop, while loops are more for interaction. For loops are more for just running a process. So anyway, wire this guy in here. And like you see, it's a different data type. So this is a double point precision, same thing. So we had a little red dot here telling us that something is wrong. So we change the representation. Red dot goes away. And what we want here is an indicator. So we want to see something we want to see what two numbers we're adding together. We can go on here and make a numeric indicator, either just the number, or we can represent it as something else. We can put a couple on here, so we can tell the number, and then just for fun we'll put a progress bar. So right now, because they're inside the box, these will get written to in every loop. If we move these outside of the loop, they will only be written once the whole loop is finished. So what we'll do is we'll put another one just outside. So we wire these things up. As soon as you kind of hover near either a node point or a kind of a VI, you'll get this little spool of wire, and that's how you wire things together. You go a little bit close to it, the little spool of wire shows up, and then you click, and then you drag. So we need to change these representations.
I have a question.
Yep.
But why
why addition want to take just integer? We want just add two numbers.
Mm-hmm.
Why it's want to be integer?
Because the input is an integer.
Or you cannot add.
You can. And it's like it was showing, it was a red dot, meaning that it's going to do it. It's just that it's not optimal. If you want to, you're essentially taking two numbers of different types and adding them together. So it will do it. It just prefers to have them at the same type, or we convert one number to a different type first. The little red dots you can more or less ignore.
So if e will be not integer, it will be okay.
So if what number?
If e will not be integer and we will add two orange lines, it will be okay.
Yeah, so if we do, so let's just, I'll show you how it changes. So right now, we have integer inputs, so, essentially we have integer outputs. If rather than stitching this guy in there, we put I'll just put another control. Okay, and if I add this guy in here, see, now it's now orange, because it's a different data type. We're going from a blue, which is an integer, to orange, which is a floating point. So, and you see here we've got a little thing saying, I don't know what I'm kind of doing, but I can do this operation, because it's got a little red dot saying, there's a little problem, but it's fine. I suppose some of it is just kind of Labview conventions for how you handle numbers. For things like this, it really doesn't matter. So, just a little hint is Control and B deletes all broken wires. Yeah.
If you wanted to add the loop number to a non-integer start number,
yep,
would you put in some kind of converter between the
loop number?
Loop number
yep.
And the. Okay.
So if I go into the numeric palette, and then I go to conversion, and then I'll just convert it to double precision. So if I now wire this guy into here, my output now is a double precision number. So if I change this representation to double precision, wire that one in there. So now it'll maintain the floating point of your start number and add an integer to it. It just requires a conversion if you want it. It'll still do these operations. It's just to make it the code as clean as possible. That's the way you would do it. You would run the converter. Yeah. We'll just create. And we'll put that dial back on. So we're now adding the loop number to some start number. We're showing it as a number, which is numeric 0. Well, x plus y, sorry, which is this one. We can change the name to some number. And then it's also going to represent it on just a sliding scale. And then once the whole loop is finished, we want to find out what that number is. So because Labview is polymorphic, there is this little thing here. So what it's telling us is that it's now auto-indexing. Meaning if I just put an indicator right there, it will not only tell me the number, but what cycle number, like what loop iteration it was on when that number came out. And it'll do it without you changing anything. So if I just go here, and go to create indicator, it'll build you an array of all of these numbers that it adds together. So you can do that, that's perfectly fine. But we just want to know the final number. So what we do is we do the same. We do the same operation, but instead of auto-indexing, we just disable it. So then, rather than getting an index set, we get the final value. So this thing just keeps running and running and running, and then the last time it goes round, this will just get fed out to this particular one. So now what we'll just do is clean up this, because this is kind of a mess. So, just like a regular user interface, you just move things where you want them. We'll put this final value over here somewhere. Move the array. It's much easier with a mouse. Some number and slider is going to occur in the middle. Okay. So we want to have, I don't know, let's do 50 loops. Where a start number of 0 seems fine. And if you look up here right now, we have essentially a green light. So we have an arrow which says we can run this. And just to show you what the broken arrow looks like, if we delete this, clean up the diagram, it won't run. It's like there's a problem somewhere. And if we click on it, it'll say that there's something is unwired. So you can actually say, show me where the wire problem is. And it'll say, look, this thing that I just made flash, show it again. This section that we just zoomed in on, it has a problem. It needs another wire. So we know that wire actually goes down here. So we'll wire it up. And as soon as we do so, we get a light to run. A convention when running for loops is to put a time delay in there that you feel comfortable with. And the reason is to not make your computer run too fast if it doesn't have to. This will run, it'll run these for loops as fast as it possibly can. And if you're trying to do lots of other operations at the same time, it's better to not make it max your CPU out just to run this. We'll run it without, and we'll run it with a time delay, and I'll show you how the convention differs. So right now, if we hit run, you'll probably see this number will instantly go to 50, more or less. It's going to be fed in through every number. So the refresh rate of the screen is probably not going to keep up with this number. Same thing with the slider. It'll be nothing, and then it'll be done. So we can just run it and see what happens. So there. It actually ran the loop 50 times. Our final value was 49 because we ran it 50 times and I starts at 0. And yeah, so now if we do the same thing and we slow it down so you can actually see what's happening. So we can just put a little delay in there. So these ones are in what's called the timing palette. And you can do all kinds of things. You can vary things depending on the time of day, or telling things how long to wait, or if they have to wait until something else is finished. But we just want to put a delay in there. So we just use this little millisecond delay. And we have to tell it how many milliseconds we want you to delay by. So we'll just say, I don't know, let's do 100. So we have no order priority on our loop, so it will run everything at the same time. So this little timer will start running at the same time that data starts to flow down these wires. This will happen really quickly, and then it'll just sit here and just count down the milliseconds. And then once this is finished, the loop finishes and it starts again. So what you should essentially see is this number tick up moderately fast and this slider scroll over moderately fast. Just a way of delaying the operation. And if we actually look at this in the back end, if we switch this little light bulb on, and then we run it, you'll be able to see how the data flows. So you see the little lights and they flow around. And all of these little boxes are telling you what number is flowing down the lines. So right now you're up to number 3, and number 4, and each time this one is saying 100 because we're just feeding it a constant. Right, and if you switch light bulb off, it'll run at normal speed. It's very useful when you're trying to debug your programs and figure out why it's going wrong. Okay, so here we have a very simple loop operation. We're adding together a couple of numbers essentially, and we're displaying the output. And for want of a better situation, this is what Labview is. You have an input, you throw in something based on a user interface, it does some things, and then it shows you the result. It does it all graphically so that you can see where all the data goes. But that's basically what Labview is. And now, knowing how we put things in, I'll kind of move to an example where we put an image in there rather than just some random numbers. Are there any questions on how we put in random numbers first? No? It should be pretty straightforward at this point. We're about to get a little bit messy.
How random are the random numbers?
Well, actually, it's not that random. There is a random number thing. It's based on the millisecond clock.
Mm-hmm.
So if I put in a random number, it's based on I think it's the sum of the last 4 of the millisecond clock. And it's based on a certain integer number. But there is a random number block. But yeah, okay. So we'll get rid of this one because that one's way too small and simple. Okay. And what we're going to do now is start an example. Let me show you what we'll finish up with first. So this is what we're going to finish up with. And then I'll kind of step through how we build it. This is a very simple VI to tell you the intensity of certain regions of an image. So we have a display window. We have something over here which is essentially the array. This is here more so that you can see what's happening. I wouldn't normally put this on a VI because it's not necessary. This is more to show you what data it's handling. And the rest is just for measuring the intensity of a particular region that we choose. So we'll just run this VI, and we have our image that comes out. It's designed so that we have this box, and we can move this box around. So if you look over here on the right, you'll see that this is, you'll see the circular edge here of the array of numbers as we're moving this guy around. And these ones all have different grayscale values, so if we move it around, we can reshape this box and then move it into different regions. Down here we have a little bit of output which tells us, okay, how big is our boxes. This is how big our box is, so if we move it, you'll see this number changes. Here we have the total number of pixels that are within this box. And here there's just a simple intensity measurement. So it's summing together all of the pixels that are within this box. So this is the kind of little program you'd write if you had a fluorescence image and you just wanted to know kind of how bright each of these spots is. This sums them all together and tells you how bright each of the spots is based on an 8-bit image. So it's quite simple. This is just the user interface that we built for it. And the extra things are down here. And I'll show you on the back panel. There's 2 ways. Well, there's 2 ways to do most things. I'm doing it 2 ways here so that you can see total intensity is how I built it based on regular numbers and arrays. And total intensity alternative is using Labview's built-in programs. So it has its own inbuilt way of telling me how intense this spot is. And it's a lot simpler to use than writing it yourself like I did here. But I wrote it myself too so that you can see what the difference is. And we have a stop button because it's in a while loop right now. we'll step through what the block diagram is, and then we'll build it from scratch. And there's no need to ask questions at this point with what the different objects are, because I'll be explaining them while we build it. So we have this guy here, which is an image holder for the memory. Whenever we open images, we need to make room for them in the RAM. So we name what we want this image holder to be called and tell it what data we're going to put in this image holder. And then we flow data into it. So this opens a file. This is the something on the front panel which tells us where that file is. That flows into this big while loop, which is why as I was moving the box around, it updated basically instantly, because the data is constantly running around this while loop with a 30 millisecond delay. It's reading this region of interest that we do. It's cropping the image to that region of interest. It's then splitting that into an array. It's indexing the array. It's summing together all elements in the array, and then it's spitting out what that value is. And the Labview Vision way to do it is there's a little box like here, a little light bulb with a rectangle, and if we go to help, show context help, you'll be able to see that instead of doing all of this stuff, you can just click on this button. And this one measures the intensities of stuff within a rectangle. It's already built into the program. It's good that you know how you do this, but when you're actually practically doing it, you just put this little button in there because it's way easier. And then this also will give you out a lot more data. So here, we're just running out the mean value and multiplying it by the number of pixels. Well, you can also get standard deviation. So if you have a distribution in these regions, it'll also give you the minimum and maximum intensity for these regions. So you get a lot of information out just with this one button. But I will show you how to do this as well as just putting this one in, because there's some times where you don't have these little programs to use. Okay, and then we do some cleaning up, and then we finish it. And then one thing to note is this little trash bin. Basically, it's memory management, so we have to put it at the end of a program to tell it to release that section of the memory, because we just allocated a section of the RAM for a particular function, and we have to then at the end of the program say, okay, we're finished with the program, you can now clear that memory off so that other programs can use that memory. If we have larger programs which use lots and lots of large images or use lots and lots of arrays, we can fill the RAM up really quickly. And if we don't delete what we're doing at the end of the program, you will not have any RAM left on your computer until you restart. So you have to clean up your program at the end. You can't just let it run. But in this case, you'd be fine. There are cases where it wouldn't be. So it's good protocol to trash your images when you're finished with them. Okay, so let's build this whole thing. And we'll do it really slowly, and it will become very apparent how we do little things. So, to start off with, like I said, we need to make room in the memory. So we're going to open up this Vision toolbar. This is where all of your little bits for doing analysis are. There are lots and lots and lots of inbuilt functions. You can click around and see what there is. Like there's machine vision ones for measuring distances, finding edges, measuring intensities, and there's ones for doing different filters and operators. I mean, it's packed with lots of things. But what we want to do is something very simple. So we just need to pull in an image. So we make room in the memory. We have to give these a name. So for now, we're just going to call it, Untitled is fine. And we have to tell it what type of image we need to make a space for. So if you make a constant, let me show you. It's asking for image type. So we need to tell it what type of image we're about to dump into it. When you start doing color images, you would use RGB color. So if you right click on here and then say create a constant, you get a little drop down and you get to choose kind of what type of image it is. Maybe it's a red, green, blue image. It might be a HSL, which stands for hue, saturation, or luminosity image. It might be a 16-bit grayscale image, but it defaults to 8-bit integer image, and that's the one that we're using.
So whenever you input some of these boxes, they basically tell you what it wants to have as an input.
If you
can
tell it to
basically
do it,
not miss any.
no.
Okay.
So especially for things where it wants a constant value, and for a lot of them, they have predefined inputs. So like for this, I didn't tell it to call it untitled. It knows it has to give it a name, and its default. I mean, I can actually delete both of these, and not wire them with anything, because it itself has its internal defaults.
Okay.
And as soon as I say, make a constant, it just shows me what that default is. Then I can change it from the default, or I can just leave it be.
So some inputs are mandatory, some are not.
Exactly. And okay, so we make room in the memory. Then we have to pull the image in. So we need to go into our little files toolkit and read file. So read the file. And if we show a little help window, you can see what it says. If we have a little hover over this thing, it changes. So if I hover over here, it'll change what this context help says. So we hover over here. What it's telling us is that to read in a file, we have to make some inputs. We don't have to wire everything. The things that it needs are the file path, and it needs an image. The image, in this case, means an image placeholder. So it essentially wants to know where in the memory should it put this file. And now it's asking for a file path. Well, we can define a file path by typing it in. So if we go to the front panel, we can go back to our just like we had numeric controls where we typed in the numbers. We have text controls where we can type other things in, strings. And we can also have a file path. So we say, okay, we want to have a box where we type in a file path. But you also have the little folder thing. If you ever click on that, it pops up a little dialog box, where's the file? So you don't actually have to type it in, you can just find it. And that's one type of file, locating the file. This will stay the same as long as you don't change it. This is a constant value. If we wanted to change it every time, i.e. we wanted a dialog box to pop up at the start and say what is the next file, there is a particular one for that. If you right click and go to your functions, you go to file input output. It happens to be in the advanced functions, but it's not advanced. It's just called the file dialog. It'll then say, what do you want them to put in? You say, okay, I want them to make an existing file, because the file has to exist to open it. So open an existing file, and then instead of having this path, you would then just wire this path in there instead. But for our purposes, we're going to use a manual path insertion. Okay, once you've got the path there, you need to display it. So what we do is we want to display something. We go to the vision toolbar and we go to image display. Okay, we can now display the image that we opened. And already, I don't even have to have this here. It says we can run this program in its current state, because we're not doing anything wrong. So we can open up this image. It doesn't show it, it just puts it somewhere. But for Labview, there's still no problems. For us, we want to actually show the image, but in Labview world, it's not a problem not showing the image. So we just wire that in. Okay. So now this whole program, all it's going to do is show us this image. So we can run it in this state. So we can just go here. Okay, let's run this program. Cool. Here is this image. We can go to a little toolkit and we can do things like zoom out so we can see the whole image. But this little 4-section thing is how you make room in the memory and you open an image.
Where did you put in the file name now?
Right here.
Well, that's where you put in the path.
Yes.
You still need the file name.
File name for what?
The file that you
Yeah, that's what we clicked on. So if I click on here, and then I just chose this example image. That's the file that I want to open.
So path includes the file.
Mm-hmm. It includes everything. Pretty big. So if I actually pull it down, you can see the full path. Or, like I said, we can switch this out. I mean, sometimes it's better. It's more advantageous because you might not necessarily, be able to easily do the file each time. So sometimes it's better to not actually have a constant in there, and instead, we say, all right, we're gonna pop up a little dialog and say which file do you want to open. So if I now run the program, it'll say which file do I want to open. Then I'll say this file, and then I'll finish.
And if it's more than one image,
Uh,
a series of images.
I'll show you how to do that. We have to learn how to do one image manipulation first. Multiple image manipulation comes next. So anyway, we'll do it just with one file name. Okay, so once we've got this image open, we want to do something with it. So we want to figure out these intensities of all these different regions. So if we go on this little light bulb thing, you can see how the data is flowing. It flows into there, it goes to the image, it finishes. And that's not very useful if we want to do things at the same time. So the first thing we have to do is put a while loop in there so that the program keeps running until we say stop. And so what we do is we go to our little programming toolkit, we click on a while loop, and we draw it around the section which is essentially displaying the image. So if we draw it around there, what it does is it reads in this file each time. But we don't actually need it to read in the file each time. All we need it to do is display the image and keep displaying the image.
Stop was this red button.
Exactly. So what we're going to do is put a little while loop around this, and then we're just going to put a stop button. Click on, get your control little bar up, and then we go to buttons, and then go to stop button, and we put a stop button right there. And you see it popped up over on your other side with a little stop button. And if we had this outside of this while loop, it would never stop, because while you're inside a while loop, it keeps running the while loop. So if you push this button as much as you want, it won't do it until this finishes. So we need to tell it that it's got to read the Boolean signal. So read if we push this stop button while it's running, and then we just wire this guy up.
In the flow of data, why did it go from the IMAQ to the file kind of disk? Shouldn't it be the other way around?
Say that again.
So
the data
when
flow.
the dots were flowing, why does it run that way? And shouldn't it go the other way?
This way?
To the memory from the file?
So what it's actually sending here is the pointer information. So so the iMac makes the space in the RAM, and then it tells this section of the program where that spot is. So it's like, I don't know, pick a number. It's kind of saying, look, at position 26 to 29 in the memory, you'll find a spot to put this. And then this says, okay, what do you want me to put in this part in the RAM? I want to put this bit of data in that part of the RAM, and then this is the representation of that. So if so this is an image, which is essentially just an array. We can just represent that as an array too. But we need this little stop button there. So if we run this program now, it's just reading this image lots and lots and lots of times until we hit stop. So if we actually click on the little light bulb, you'll see where the data is. It's reading in this image data in every loop, and it's reading what the stop button says every loop. So right now it's reading false because we haven't done anything. But as soon as we hit this button, it'll read true. There you go, true, and then it stops. And this is important for when we want to actually do things like moving around this region of interest. So if we run it again now, take that little light bulb off. We can actually do things with the image. So we can draw a box. And we can move this box around now while the program is running. So if we pull out the data for what this box is, we'll get it in every loop. If we weren't running in a loop, then it would only read the current position of this box. And I think right there, I'm going to stop so I don't kill you guys, because it's been an hour. Unless you would like me to continue. Would you like me to continue? Maybe take a break?
Yeah, really. It's
Room is very small.
Okay. We take a break, and then I will show you the half of the program which uses the Labview VI. So the simpler way to do it that you will undoubtedly use, and not this way of doing it. So this is basically what's inside this little program. It's a long-winded way of adding all elements in an array, and this program does that. So we don't need to reinvent the wheel. It already has the sub-programs in there.
So you will go from that to this.
Exactly. Because we don't need.
Skip all this.
I can skip this, and then there will be times where you'll need it.
Okay.
And for this example, you don't.
Okay.
There are, like I said, it's a very, very rich toolkit within Vision. It does lots of predefined functions. Here I'm writing it out in full so that you can see how you would do this if there wasn't this inbuilt, so that you can see exactly how you would index an array, how you pull out different parts, how you would add bits together. It's an important thing to know, and kind of going back to the previous comment with Ilya. So like here, I have to convert my numbers, because when you're adding together 8-bit integer numbers, if it's still an 8-bit integer, you can't have. It doesn't matter how many times you add it together; it just keeps going back to 0. So you have to change it from 8-bit integer number to a higher bit integer number, and then it can add together, and then you get bigger numbers. But you'll come across these kinds of things all over the place where you need to convert. Same thing with images. Sometimes if you want to do, let's say, an overlay on the image, like you want to draw like a particular box or a colored box, or for the stuff that we did with Alar, where we had colored lines constantly measuring different things. You have to convert a grayscale image to a color image because you can't put colored objects on a grayscale image. It'll say no. So then you have to do these kinds of conversions as well, where you're like, look, this is now a color image. But we'll pick up in a little bit, and then I'll show you the second half of how I put this together.
Now we show you.
Yep. Okay, and we're continuing the confusion fest. So, just to reiterate where we left off, Labview has an awful lot of inbuilt virtual instruments, or VIs, that can do very complex things. And here I'm just showing you 2 ways. This is the manual way. So indexing arrays, summing together different elements. Or you can use inbuilt functions, which is this one, and I'll show you where it is in the tool palette. And this is the one that we will use for our example. So let's just pull up our example again. And yes, this one. And we'll just show our block there from panel 2. Okay, so where we left off is we have an image, and in fact we'll run it in light bulb mode so we remember where we are. So all the data flows down, flows in here, and it keeps running round and round and round. And while it's running round and round and round, we can do things like draw boxes. Boom, draw box. When we hit stop, obviously it stops. You get a false command, you get a true command instead of a false command, and it stops. So we can switch our light bulb off, and now we can do something with this data. So like I showed you, there are inbuilt functions for measuring intensities. So I will show you exactly where they are. So the intensity, some of these things, the only way to know where they are is to look around. There are lots of different functions from filters and of things in the processing, different color things, frequency domain things, so Fourier transforms, and particle analysis is in there too. In vision utilities, it's more like reading single point data and manipulating the actual files. But what we want for the intensity is actually in machine vision. So it's in a folder called Measure Intensities. So we click on that one, and then in the Measure Intensities folder you have a few options. You can choose to give you a point intensity, a line, which essentially is a line scan, so you can tell it to output a line scan, or you can tell it to just give us a region and tell us what the intensities are in that region. So that's the one that we want. So you click on it, and then you can put it on your panel somewhere. Okay. So if we pull up the context help, we can see exactly what we need for this little program to run properly. And you get a little description too. It says it measures the pixel intensities. What it requires is an image, a rectangle. In this case, it wants essentially 4 points. It's a brown data line, which means it's a cluster type. So we have to build a cluster for a rectangle of the image, and the coordinate system is optional. We don't need it. What it's there for is if your image is rotated or your box is rotated, we can say, look, we want to change the coordinate system from being a standard XY to having some rotation factor on it. And error in and out. And error analysis we'll touch on next time. They're very important and very useful, but I don't want to confuse people right now with errors. So for now, we just have to simply stitch in two inputs, the image and the rectangle. And you'll also notice that they're bolded. Something I forgot to mention before is if there are VIs with optional inputs, then the necessary inputs will be bolded, and the optional ones will not be bolded. So here we can see, okay, it really wants the image and the rectangle, but everything else is optional. So those are the two things we need to wire in. So let's make our box bigger so we can see where we're working. So while we're in this for loop, what we want to do is on this image, which is the image that we're looking at, we want to measure something. On the front panel, you have all of these tools, and we can switch these tools on and off. You have a magnifying tool and a pointer tool and a pan tool. They all do differently. It means that you can move around the image if you're too zoomed in, for example. Line drawing tools and all the rest. They're just what they call the image toolkit set, and we can switch them on or off. They're always on by default, but if you right-click, you always get lots of different choices. Here we can choose the visibility, and we can switch them on or off depending on. A lot of times it's kind of better to just switch on the ones that you need so that you don't accidentally push the wrong one in the middle of a program. So we want the zoom tool and a pan tool, and we'll have a rectangle tool too. Okay, so now those are the only options we have. And once we're in the rectangle tool, we'll be able to draw this box. And what we need to do, what we need to feed into this VI is the positions of these two corners. So we need to get the output from this user interface section and feed that back into this section. So if we right click on image, you get a series of options. What we want to do is we want to create a property node. So we want to get a bit of information from the front panel. And the way that you do that is you create a property node. There's an awful lot. There's an awful lot. And I want to say 95% plus of this you will never touch. You know, it's kind of like questions. Do you want the cursor to be blinking while you are doing it? You know, do you want to be able to? I mean, it's these kinds of things are what you have options of. There are things which are very useful, like for example, this 16-bit mapping. If you're showing a 16-bit TIFF, for example, if you open up in an image analysis program, it'll be black because most programs don't know how to handle 16-bit images. And what you can do is tell it how to interpret that image and show it, because the computer screen is 8-bit. But what we need for this example is we need the ROI, so the region of interest. So if you scroll down to the bottom, you have some options. These one, it doesn't really matter in the grid size. You don't care about the color. What we actually just want is all of the core data from this box. And that's what we have here. And again, just like with the other VIs, if you hover over it, in the context help, it tells you, what it needs or what it does. So here it's saying, in this data stream, this is what there is. You have a cluster of 2 elements. So if I open up this data stream, we should see a cluster. So if I go to our cluster palette and tell it to unbundle this cluster, in other words, break apart this cluster, it says there's 2 parts. And if we go back here, that's what it says. It's a cluster of 2 elements. We have a global rectangle, and a global rectangle is a 1D array. So it's a 1D set of numbers. So 4 numbers in a line, essentially, saying xy of this point, and then the xy of this point. And then there's a lot of other stuff in here, but most of it you don't particularly need. It tells you the contour type. So this is a generic bundle of data. So if rather than a rectangle, let's say we had a circle. Well, knowing the global rectangle only tells you the outermost points of that shape. If it's a circle, that's not always useful. So then you have to go into this second section of the cluster, which says, okay, what type of region of interest is it? Is this a rectangle or is it a circle? Where are the points for all of these things on a circle? So there are different types of data in this parameter depending on what you've chosen to draw. Because we're drawing a rectangle, which is the simplest form, we only need to worry about this first one, which is a nice 1D array. So that's what we're going to handle, is this 1D array or global rectangle. So we go back over to our little light meter, I think they call it, yeah. And we look at this rectangle. Sometimes we'll click on help, so we can actually see, okay, what it needs. Okay, this is just the help menu for it. You click on, just in case you didn't see me click on it. Here. You click on the detailed help button. If at any point you want more information about that particular thing, if you click on there, you get the help menu pops up. And it tells you a whole bunch of things. But what's important to us is we have to know, because this is an inbuilt program, this isn't something that we're writing, we have to know what shape or what kind of cluster it wants for this rectangle. Now in this case it wants them in this order. The left x coordinate, then the top coordinate, the right, and then the bottom coordinate. But it also wants a rotational coordinate, because this is what it calls a rectangle instead of a global rectangle. Global rectangles don't contain rotational coordinates, whereas this one, it can run, because it can have a different coordinate system, it also wants to know what the angle is. So we can close this. So we now know we need to make a cluster. So we need to make a cluster, and the cluster has to be 5 elements. And if you're ever unsure, just like we could do with the iMac, so just like we could just click on create constants with these to see what the default value is, you can do that with things which don't have defaults. It'll just show you what types of data it expects. So if we click create constant, we can see, okay, it's expecting 4 integers and then a floating point number. So we have to make sure that we give it 4 integers and then a floating point number. So we can delete that and we'll build our own. So we go to cluster, and they call it bundle for building a cluster. So we need to bundle together 5 numbers. You can just drag these points up and down, changes how many inputs there are. We need x1, y1, x2, y2, and then a rotational coordinate. I mean, we know the rotational coordinate is going to be 0 because we don't want to rotate it. So if we go to the numeric palette, we can just make a constant value, and we can just call that one 0. We don't want it wired there. We want it wired here. Okay. So we also want to change this representation to be double point precision. In these ones, we now need to put in what we're getting from our box, or this little region of interest that we're drawing. So this one outputs region of interest. We're then unbundling this cluster, and then we get a 1D array. So what we have to do is we have to index the array, index this 1D array for each of those 4 points. So we have a little array palette. We can do a whole series of different things with arrays. But what we want to do is we want to index this array. So we pull it in. And then we want to know what each of these 4 points are. So we want to be at point 0, 1, 2, and 3. Let's make some room. So we just create constants at each one of these points. So Labview always starts at 0. It's something you'll kind of get used to. Loop numbers, array numbers, everything always starts at 0. 0 is the first thing for Labview. So we index the 0 element. We're going to index the first element, the second element, and the third element. Okay. So now what this is going to do is output here. Yeah, good point. Each of these element values from this 1D array. And we know this 1D array only contains 4 things because this thing tells us that's what it contains. So we can wire these values into our cluster. So we wire it. This one, this one, this one, and then this one. Now the question on everyone's lips is, how do I know that's the order to put them in? Well, because that's what you learn. If you what I would do is put a little indicator here. So if you right click and then go to create indicator, it creates this little array. And then as you're drawing this box, it's going to change these numbers. So you're going to find out where x1 and y1 is in your global array. And what you'll kind of come to learn is that all global arrays go x1, y1, x2, y2. That's just what they do. And you get very used to that, so I know that if I take a rectangle and I have to wire a global rectangle into it, everything is the same apart from this rotational component that we just stick in a constant as 0. And right now it looks a whole mess. So ordinarily, I would have to, do all this kind of things and then clean it all up, make sure everything's in the right position, and make it look all pretty. But they realized that when you get to very large programs, and if any of you have seen programs that I write, they kind of get large. They figured out it takes way too long, so there's actually a button that you can push and it cleans it up for you. So you push one button and boom, oh, it's all pretty now. And it just cleans it up so you can follow it much easier. And it's probably one of the nicest changes they've made over the last many versions, is just that simple push a button to make it clean.
Which button is that?
This little sweeping brush here, clean up diagram. Because, this, it's a little bit messy. And when you start having these wires going forwards and backwards, and every now and again, it's just good to clean it up and then go from there. So, looks much simpler again now. And we'll just, a lot of times it puts things a little bit too close together for how you like them, so you can spread them back out a little bit. But, okay, so we have this cluster now, which is what this guy wants. So we'll just wire this cluster into here. Okay, and we got a little red dot. So this red dot means one of our data types is wrong. So what I'll do is just double check what data it expects. So it's saying 32-bit I, 32-bit I, double point precision. So I don't know why it's complete. We'll ignore it. So you have the option of having an image out. So if you were going to be drawing things on the image while you're doing things, you can flow the image through this VI into another one. But all we really want is we want to see the gray level intensity. So we want to have some indicator. Okay, so I just create an indicator, but this is a cluster. Okay, and that's kind of what it's saying here is there's a lot of things that you were expecting me to show. So if we look at the front panel for what this cluster is, let's close down some of these things. It's down here. So it popped it down here. So this thing that we just created is down here. And what it's giving us is these bits of information. It's saying that within this data stream, it tells me the mean, the standard deviation, the minimum, the maximum intensity. But what we wanted is this, but we also want to know what the sum of the intensity is. If we choose a region, we want to know how bright that entire region is. So we have to add it together. And we can do that from the mean, but to do that, we also need to know how many pixels there are in that region. One thing that we do know is we do know how big this global rectangle is. So we can use this global rectangle information to calculate how many pixels there are, and then we can multiply that by the mean, and then that will tell you what to multiply the mean by to tell you how many what the total intensity is. So x1, y1, x2, y2. Calculate the number of pixels by finding out the difference between x2 and x1 and y2. And y1. Okay, that tells us how many rows and how many columns that there are within this region. And then we just need to multiply these two numbers together. So that's what we do. Multiply you there and you there. So then this becomes the total number of pixels. And we can just give a little indicator for that. So we create an indicator. we can name this total number of pixels. But one thing that you'll find as your diagrams get really big is sometimes it's nice to actually label the wires. When you have lots of sections where data is flowing from one side to the other, sometimes it's good just to say what's within this wire. So this wire is number of pixels. Okay, so to actually write on the screen at any point, you just double click, and then you get a little kind of text boxy thing, so that you can put lots of annotations in there. If you leave it here and you click cleanup, it will try and put it in the most favorable position, but most of the time it's going to be nowhere near where you want it. What you actually need to do is put it on top of the wire, at any point on top of the wire, and then it will always, when you click cleanup diagram, it will always keep it on top of this wire, so that you know number of pixels is in this wire. Okay, then once you know the total number of pixels, we then need to multiply that by the mean intensity. So if we go to context help, and we kind of hover over the wire, it tells us what type of data will be within that wire down here. So it's saying within this wire, it's a cluster of 4 elements: mean, standard deviation, minimum intensity, maximum intensity. So if we unbundle this, so go to our little palette, go to cluster, unbundle. And for a lot of these functions, it will actually maintain the name of the indicator when you do bundle unbundle. So it's not like an array where they're just index numbers. In bundles, they actually maintain the names. So you can see here that mean intensity is right there. So we now need to multiply the mean intensity by the number of pixels. So I'll multiply this guy. Like this one. And as you can see here, I'm not converting this because I don't have to. I know this number is going to be an integer number because the image is an integer number. So I don't need to convert it. And then just put an indicator. And this is going to be total intensity. Okay, so we can look at this diagram now and see where we're at. Maybe we should clean it up. And as you saw when I click clean up, because this is written on top of the wire, it keeps it on top of the wire. If you just put it in the image, it'll move it kind of wherever it pleases. Okay, so data now will flow down here. You'll get an image. That image will go into this VI for intensities. We'll draw a box on our image. We'll then find out the X and Y positions of that box. That'll then be compiled into a rectangle. This will then read that rectangle, output data from that, mean intensity, standard deviation, etc. We'll then pull the mean intensity off. We'll multiply that by the number of pixels that are within our little rectangle. We'll then be told what that intensity is.
That was the icon that you said it sums up everything, but I didn't remember. This
So,
one with the
So
bar.
this program now does exactly the same as this one. Both programs do exactly the same thing. It's just that here I'm showing you that there are 2 ways, this way and this way. And if you look at, so this one is a lot smaller now, because we're using an inbuilt VI to do what inbuilt VIs are designed to do. They're designed to make your life simpler by pre-programming in all these kinds of different things. So we're now using this to get the same amount of information out. So we'll go to our front panel, the user interface, and we'll make sure that we can see where things are. So we'll move this and oops, move this one over here, and then this one. Okay. So So what we'll get when we draw a box is we'll get out the statistics for all the pixels within that box, and then we'll also get this little statistic that we're writing ourselves, which is how big our box is, and also what the total intensity is within this box. So if we run this program now, hopefully it won't crash. Okay, so right now it's running, because this arrow tells us it's running. And if we grab this box, everything should kind of move in real time. And what you'll notice is that we're dragging around this kind of green trash. And what that is every time we use the kind of, let me pause it. So every time we use this function, what it does is it draws a box on top of the picture so that you know where you're actually pulling out information from. And right now, we're not saying get rid of that box. It's just drawing it. Every time it goes around this loop, it redraws that box. So what we can do is tell it, okay, we need to trash this box because we don't want it displayed each time. So if we go to Vision and Motion, back to this toolkit, go to Image Process, Vision Utilities, sorry, go to Overlay, and we tell it to just destroy the overlays. We don't need to see where we've been drawing. It's not necessary. So we just say, just destroy the overlays. Let's say we're doing it on this image. And I notice I'm using the image out to actually wire the destroy. The reason I'm using the image out and not the image in is if I wire it to image in, if I wire this destroy overlay to image in, it has essentially the same order priority as the draw the box in the first place. So the data will stream down here. It'll come down here, but at the same time it will go down here. So you'll have an order problem. The order is wrong. We need to fix the order. So there's two ways in fixing the order. One is, well, we can just wire it to the image out instead, so that, like we said kind of in the presentation, this VI will not start until it has all available data. So this VI has to have run first before this one can run. And there's other ways of doing that. And one way is to wire the error up. So this now is dependent on this VI finishing. So by having this data stream here, it's kind of linking it and saying, look, you can't do anything until I have data from this one. So there's just two ways of doing the same thing. Okay, so now we're destroying the image after each run. So if we do the same run, window, as we move this box around, you see it no longer drags a green box with it. Because now every time it goes around the loop, when it finishes figuring out this information, it destroys this green overlay. So if we slowed this down an awful lot, what you would see is it draws this green box, measures your intensities, the green box disappears, and then when the loop starts again, it draws the green box, it does its thing, and the green box disappears, and then it starts again. It's just running so fast that you can't see it destroy the green box and then recreate the green box. But every time it goes around this loop, this green box goes away. But now what you'll see is as we move it around, all the numbers kind of change as you'd expect them to. Total intensities kind of get really high. The number of pixels stays the same unless we redraw the box. Woohoo. Unless you draw it outside of the image and then it crashes. So I'll show you what we did. So, let me draw it again. I know. So, the box ended up outside of the image area, and then it said it was drawing, let's say it's x1 or x2, sorry, was bigger than what the image could be. So it's like, I don't know how to handle that because we haven't put any error analysis into here. We're not telling it what the range of values is. We're just saying, read whatever values we draw. So if we don't put in any error values, if we drag this box off the screen, off the image, the y values and x value for this point now are non-real. So it just crashes. It basically says, I have no idea what that value is. We can put limits and bounds on what these values can be. We can say y2 can only be between 0 and as big as the image. And if it's bigger than that, make it equal to the largest value. But right now, I don't want to show you how to do that. We'll just show you how to put these boxes on there. But if we run this program, essentially you have what I did originally, which is pull data off your image. This is the data we're getting. This is the data that we asked for that was extra. And it'll run basically real time. We can make lots of changes and draw off the screen if you want to. We can make lots of changes in real time. But one thing that we're not doing right now is the thing that I said we absolutely have to do, which is destroy our image. So, outside of the while loop, we put a little trash can. Hey. Where the trash can. With these, lots of times if you have lots different images, you might want to destroy images at different points. We're only making one, so we can wire this image name straight into there if we're being nice. The other option is, instead of wiring that image in there, is say, look, you know what, my program at this point is finished, so I don't need to mess around, so we'll just destroy all images that are made in this program, and it'll just wipe all of these IMAX that you've made in the whole program. It'll just wipe them out of the memory, so it frees the memory back up. Other things to make it more compliant to how computer compliant, should I say, is to put a little delay sequence in there so that it doesn't run the loop too fast. So CPU is not constantly running at maximum rate. You can't see any faster than 30 frames per second, so there's no need to run the loop faster than 30 frames per second. The computer itself is probably running at a couple of hundred frames per second, but you can't see it, so you moving the box around doesn't need to be any faster than what you can physically see. So put a little 30 millisecond delay in there, and then your CPU is much happier. So if we run it, there's no change or no delay in how you do things, because we're only seeing a certain frame rate. Your computer doesn't need to run any faster, but your CPU usage will be much lower because we did that. Make sure we find the stop button. Okay. So if we hit stop, the image will go away, which means that we've coded our image destruction right. It's deleted that image from the memory. We're not wasting space. And you can just clean things up. Like, we don't need this guy. We don't need to see what that rectangle is, for example. You notice now that you've got a little broken thing, we can say, show me where that broken thing is, and it shows you here. It's saying there's a wire just hanging out doing nothing. So we can just delete that wire, and then it's all happy again. Clean it up, and then just save it. And then you have a region of interest analyzer for images. Questions? Just how confused are you at this point in time?
It was a bit intense, I think.
Yeah, for me it's too much.
No. So kind of like I was mentioning at the start, the goal of at least the first session and most of the second session is to not get you to reproduce it. I don't expect you to reproduce it. It takes longer than that. It's so that you can read it. So that I can hand you a diagram like this, and you can be able to see instantly, oh, okay, I know this is a purple line, and I know it's wired to this block that looks like a picture. Okay, I know that is outputting the image into that block. I know what this kind of blocky thing is that has some numbers going into it. Well, we're talking about, that means index the array. So I know at this point, we're indexing an array. That's more what I think you should be able to look at, is look at the block diagram and understand where data is flowing in and where data is flowing out. Reproducing it at this point is too hard. I mean, I don't expect it. I mean, it takes a long time to know where all the tools are. But equally, I can't teach you where all the tools are, because there's millions of them. You know, all I can do is take an example like this of drawing an image, show you what order of things that you would do to get that out of the image. And then, you know, because you have the video, you'll be able to see where I got these parts from. You'll be like, oh, I had to figure this bit out. You look at the video, oh, that's in this toolbox. Most of the toolboxes are pretty self-explanatory. And because you're centering around image manipulation, they're almost all within the sub-toolbox of vision. So if I trash this, and you right-click on the screen, you get, these are all of your toolboxes. And from here, we have, you know, like down here, you've got your array. So, you know, that's in the array palette. And, you know, the clusters are in the cluster palette. But for all of these kinds of tools that have to do with image, they're all in this vision toolbar. These signal processing and measurement and instrument stuff, they're all good to know. And at some point, you'll come across them and need to use them. But to start off with, they're things that just exist. It's a little bit different than a regular programming language, where if you don't know what the command's called, it doesn't confuse you, because you'll never call it. You know, you won't type in, like, I don't know, do some fast Fourier transform, because you'll never see fast Fourier transform unless you know the code for fast Fourier transform. Whereas here, it's a button. So in a way, it confuses the interface, because you can click on it at any time. You just don't know what it does. So in that sense, it can be a little bit overwhelming. You kind of stick within the palettes that you feel comfortable, and you know what you need to pull out of them. But what we want to get out of these initial couple of kind of demonstrations is data flow, what different icons look like and what that means, and, you know, kind of how we make small changes. Like, for example, if, I don't know, we wanted to do something with the standard deviation instead of, you know, this mean value. You know, we can grab here and, you know, make a wire and wire that to something. You know, we can just pull it straight out. So we now have the standard deviation, and it's running to the edge of our loop. Well, if we right-click on that, we can index it. It's going to be bad. So then what we have here is we're going to build an array of all of the standard deviations from every loop in the cycle. It's going to get real big. It's generally not good to run indexes in while loops, because they're dependent on your array. So you can build, I mean, we're running at 30 frames per second, so 30 times a second, so every 30 milliseconds you're making a new element. So if you're sitting here doing something for 30 seconds, you've made 30 times 30 size array, and it's not generally good, which is why it didn't come up as a default. But yeah, don't worry if you're confused at this point. That's totally natural. And in a way, it's good, because it'll make you want to look around and dig at things, because it doesn't make sense. Hopefully what I'm conveying is that with a small subset of commands, you can do something quite complex. And for whatever there is, maybe 20 different connections that we have here, we actually have a whole program which analyzes an image, which for a programming language is very minimalistic. So
What is the, sorry.
Which button do you try to get out of the function now?
to get out the function,
Yes, which button do you press
to get the tool palette,
Yes,
right click.
Right click. And when do you give the next section?
It depends when you guys have time.
We need time to digest. Me, I did not, but otherwise I don't see the point to continue. So
No.
me, I prefer, like, I don't know, in 10 days. because we have something else to do, you know, and yeah, I need to watch again the video and
Yeah,
digest.
it's there, you know, so right now, because it's still recording, there's around about, I could probably stop it, but there's about an hour and 45 minutes of video here.
Yeah.
So,
And repeating those, you know,
Yeah,
trying to really.
yeah, maybe in 2 weeks, I don't know.
Yes, but it's better to tell us in advance so we can arrange our experiments or
Yeah.
right,
other things.
so why don't we say, so right now it's the 13th.
Yes.
Yes.
I don't
So-
know everyone's schedule, but can it be a Monday? Because Monday is already half day is gone, and
Okay.
the other half day no one prefers the book, so we can take it
Yes, that's good.
on Monday and
Monday,
then the rest
25th.
on other days.
25th?
Yeah.
Oh, I have exam on 23rd.
But 25th.
Ah, 25th.
On the Saturday?
21st.
That's good.
You have it on the
I'm
Saturday?
sorry.
Yeah, I have two for another course, for example. It's very common, I think, in Chinese.
Thank you for that.